All right. So, are there any pressing questions before we get started on the review? Yes? No? When is the final? Friday. Where is it?
Here.
Okay. What time?
Noon to 1:45.
I think that's right. Yeah. I had it in the last lecture. So. Anything else about the final that is not clear?
This lecture is 28 to 32, correct?
That is correct. Yes. And as I said, the old finals are on the website on Carmen. All right, so we're going to start in reverse order and start with the lecture we just had. And so this is a more advanced treatment of conductivity in polymers. And we have to think about how do we overcome some of the natural insulative character of normal polymers, in which we know we rely on all the time, and now we want to turn it around and invert that somehow. I encourage you to review the end of lecture 16, which it's only actually a small part of the overall lecture, which a lot of it's on the carbon-based conductivity and polyethylene. But lecture 16 covers some of the background concepts, specifically crystallinity, especially, that is important in this context. And so this is something that we need to know because we want to know how to control conductivity in the real world rather than in a laboratory somewhere. And so the limitations between the real world and the laboratory are pretty extreme. And potential applications, you should have some level of familiarity with it. There's that one slide that talks about where it could be useful. And in some areas it is useful for those applications, and others, well, it's just a dream right now. And a lot of this needs to focus on what are the roadblocks to applications. Why can't we get to copper-like levels of performance from these systems? Maybe someday, and things will be quite different if we could do that, but right now we're not there. Okay, and then where it gets really interesting is in these polymeric light-emitting diodes, or OLEDs, like the one I hold in my hand right now. These are examples of how we've been able to take this process, as inefficient as it is for matching copper, and find ourselves a very, very useful application that gets rid of these enormous, heavy glass screens we used to have to deal with. And so, in that context, you need to know what the basic structure of these devices is. How does it work? So these multi-layer systems that we put together that involve that polymer layer as a key component where the excitons can form and then annihilate, and all that process gives us what initially was pretty crappy looking light, but now 20, 30 years later, we've got this technology that has totally supplanted the old CRT tubes that used to be everywhere. And so, in that context, how does that process work? How does it relate to mechanisms for conjugation-enabled conductivity? So, again, it's not copper, but we can still get the type of behavior we're looking for in this context and in these very thin films and in many, many tiny little elements. We get this type of behavior. We get TV screens. So it's really amazing. There are some similar stumbling blocks as before, so you should have some sense of what those are. But for what we're doing in the context of these types of devices, it's relatively good. And it is something that you need to be aware of is the device structure and wavelength control and the use of filters that are applied to these RGB units. All right, and so RGB, red, green, blue, that's the basic structure, basic idea of color for a lot of different applications. And in this context, we've been able to do some remarkable things with very simple devices when they're present in thousands and thousands of units. And you can expect an abstract in this area because there's a lot out there. And I know last year's test, that's why I'm still searching for it. I had a great abstract on there, which I guess maybe I can resurrect if I can't find that old test, involving optimizing the behavior of these types of OLED materials. And there's always a huge race to come up with the next version of this and make them smaller and have, it's 4K now, 4K TVs, and next is going to be, I'm sure, 8K TVs, and then who knows, 800 kV TV. It just gets going and going and going. All right, any questions about that? All right. Next up is polymer viscoelasticity. And why are polymers viscoelastic? And so this is a word that we use that captures both ends of the spectrum with polymers. And you guys, especially now, should have an appreciation for both ends of those spectrums, how polymers can go from being viscous liquids to being highly elastic materials. All right, and so you now have a good appreciation for, normally we just say, oh, it combines elements of viscous behavior and elastic behavior. You should have really good appreciation for those different elements and how the structure and control of molecular weight of polymers can get both ends of that range. All right, so that should be very familiar to you. And as always, I'm looking for a molecular motion-based understanding. All right, so being able to make sure you have a grasp of those concepts and how those can control the behavior of these polymers, particularly as they flow, all right, and also in terms of their mechanical properties, is going to be important to us. And we're looking at understanding the behavior and consequences of this, and then also the concept of permanent set. Everyone knows what permanent set is, correct? All right, this kind of feeds into the whole issue of creep, especially in stress relaxation. All right, so this permanent set concept, what it really means and what governs it, is going to be important to us. And then, of course, kind of the upfront aspects of this, creep and stress relaxation processes. What are they? How are they examples of viscoelasticity? So, and you'll see this on the old test, at least one of them, I think. I just flat out say, okay, well, here's an example. What happens? Why is it happening? Why is this being governed by viscoelasticity? You should be able to come up with some reasonable explanations for all of that. And then we have simple time temperature superposition principle calculations. So we will have some of these quantitative problems on the test. Not as challenging as midterm 3, much simpler. This is probably the most challenging one, but the rest of them are pretty straightforward. And you need to understand how viscoelasticity versus temperature behaves, which again relates to molecular motion, which again relates to how quickly change can move, all right, and be able to understand as we go up and down in temperature what happens to viscoelasticity. All right, again, you understand a lot of this background issue now, and so these things should be familiar to you. And simple WLF calculations, new viscosities expected at different temperatures. Make sure you understand the math of working with natural logs. Sometimes people forget how to do that, so you want to make sure you go back to the example I worked out in class and how to understand how to manipulate these equations when it comes to natural logs. Every year it's like, oh, I forgot how to do that. Well, it's pretty straightforward once you refamiliarize yourself with it. I know you've all had the math. All right, I'm sure it's somewhere back in your early days you've done this, so it shouldn't be that hard to pick it up again in case you're not familiar. And then molecular weight and viscosity. What are the effects and why? All right, so that's something that we talk about the physical properties of polymers, and this kind of gets into liquids. All right, and there's a whole range of things we could talk about. I used to have multiple lectures on injection molding, and I don't do anymore. But in that context, we deal with this issue of liquids, polymers as liquids, and how we can manipulate them. And a lot of what we learn for solids relates to liquids. PVC viscosity is higher than polyethylene viscosity. That should not be a big surprise to you. Right, take away all the crystallinity, take away all the solid structure, and we still have the same type of mechanisms governing the behavior of those melts. All right. And in this particular concept, we kind of stick a toe into the issues of injection molding, and one of the reasons why it's so difficult, or can be very difficult, and what goes on here at the wall versus what happens in the middle, and how they are very different from each other. All right, so we're all familiar with that. What's the velocity at the wall? 0. Okay. So start from there and look at this concept as a series of different layers being sheared relative to each other. And obviously that must be a pretty substantial amount of shear because this guy is going down there and making a part. This one's not doing that. All right, so obviously there's a ton of shear in these systems. And so that helps guide us in terms of understanding what can be molded and what can't be molded. And then some of the other factors that are part of this as well. A shear rate, why is it a maximum at the wall? Why is it a minimum in the middle? And same holds true for shear stress. All right, so those should be pretty straightforward parts of your understanding at this point in time. Any questions so far? All right. Simple calculations involving the critical chain length Z sub CW and temperature control of potential process line. I know there's the polystyrene cups on one of the old finals on the website, so that's right out of the class notes. So you have a look at that, make sure you're familiar with how to do those types of calculations. And we also think about polymer rheology. You know, rheology in this context is the study of viscosity in these systems. And as I've always said, the chemical engineers kind of pick it up from there and treat everything as a gray continuum with no real recognition of what goes on inside of it, but they can model the hell out of it, so that makes it good for them. But you know, we understand a little more detail about what's going on inside these systems. And this issue involves, of course, the shear flow of polymeric liquids, because, of course, there's a ton of shear going on up here. And in that context, we recognize that many of these are non-Newtonian fluids. All right, water is our only Newtonian fluid, and it's a wonderful thing to make assumptions about. But in this real world, we're talking about polymeric systems that exhibit either shear thinning or shear thickening. And this has to do with, again, the polymer structure that's going on inside these systems, and issues of molecular weight. You know, those should be obvious factors in this concept of shear thickening or shear thinning. Bonding, secondary bonding, presence of polar groups, bulky side groups, all those things factor into flow here as well. All right, so what you've learned for solids still applies to liquids in this context. And then Brownian motion and entropy. All right, those haven't gone away either. And Brownian motion in this context can be have pretty strong effects, and of course entropy is something that the system always wants to get back to. All right, and so obviously all this shearing that goes on in these systems means that we have some type of alignment going on somewhere. So the system wants to get away from that. All right, and remember the concept of die swell. I think I talked about that briefly. It's a great example of how the system doesn't like being aligned and tries to get away from it if you give it half a chance. Okay. And then viscosity and chain alignment and entanglement and disentanglement effects. You know, clearly those should be important in this context of flow as well. All right. And so, again, what we think about in terms of the mechanics of solids also applies to this kind of mechanics of liquids, is basically what this is. All part of the viscoelastic theory. All right. Any questions about that? Seems clear. All right. And then lecture 30 was polymer mechanical properties. I kind of call that part 2 here. So you guys have already learned a lot about mechanical properties of materials, and polymers especially in this class. And we go from the things that you've learned elsewhere in the department, Young's modulus, tensile strength, and now in the case of polymers, we're talking about some different aspects of elongation to break, in which polymer structure has a very strong control over that. We don't normally think about this with, they're certainly not ceramics and often not metals, because again, by the time it fails, the plane has already crashed. But in this context, we can have some utility in terms of elongation to break, because it reflects on the other component of polymers that's really important, which is toughness. All right, and so in some sense, what we used to think about in terms of just the inorganic side of things kind of has a counterpart in terms of this toughness-related aspects. And so this is something that I still see on the tests where, I can have a high modulus and a really low toughness. All right, so don't tell me the mechanical properties are improved, because I'm confused, because toughness is a mechanical property, Young's modulus is a mechanical property. I know they don't both improve at the same time. All right, so this is why you can't be generic about saying mechanical properties. Or you say what property you are talking about. Young's modulus, or you're talking about toughness. So make sure that you are aware of the fact that these can go in very different directions. It's very difficult to improve both of those things. at the same time. Okay? And then be able to recognize and construct stress strain curves for different plastic conditions. So if I give you a problem and say, okay, we're forming this material and it behaves in this way, and then we hit it with some gamma rays and we lightly cross-link it, what's that going to do to this process? How is that going to be dramatically changed by the addition of even just light cross-linking, which will certainly make a huge difference. You should be able to see why that's so important. For one, flow down a tube becomes really, really hard if you have even a small amount of cross-linking, because all those polymer layers can't shear by each other anymore, for example. Okay? Any questions about that? All right. And then getting into some other aspects of what goes on in these systems. We talk about polymer yielding, and we talk about these terms we borrowed from metallurgy: cold drawing, strain softening, strain hardening, and also, lest we forget, the clock model. All right, all this stuff rears its ugly head again, and we need to know what these terms really mean in terms of the polymers, the polymer behavior. And so we're not so interested in talking about dislocations here. We're interested in talking about polymer chains moving past each other. We're talking about what happens inside the gauge length of these materials as that microstructure or that architecture is destroyed by the process of being sheared during the deformation of these dog bones. And so we have this advanced view of the inside of the gauge length of a dog bone now, in which there's a shearing process, the destruction of microstructure, and then that propagates down the length of the dog bone. We start at the neck and move down. All right, so you guys should have a much better understanding of what goes on in these systems and how the crystallinity, spheroids, everything that's in the system is going to be influenced by this process. All right, any questions about that? Everybody knows everything. We're all good. Okay. And then the elastomeric behavior component of the special case of natural rubber, in which we have some kind of unique things going on. So rubber being one of the original plastics or polymers that we started to learn things about. And it's still very important to us technologically. And so we know some things about rubber that are kind of special to it. And then make sure you're ready to discuss the effects of any of the following on mechanical properties: molecular weight, branching, cross-linking, crystallinity, plasticizers, polarity. I think some of us are still fuzzy on that one. Chain orientation and rate of deformation. All right, so this is your chance to demonstrate that you've learned this much about plastics and how they behave and how you would expect them to behave as any of these variables change going forward. So there are a lot of design issues associated with plastics, and any one of these factors can play into those design issues. So understanding and appreciating what those can do is going to be important to us. And this is just showing you this effect of molecular weight, how we get beyond a certain length and we get to entanglement where we didn't have it before, and everything changes. All right. So we see this for mechanics. We also see it for viscosity as well. All right, we go from a slope of 1 to a slope of 3.4. All right, so molecular weight makes a big difference for these materials, whether liquids or solids. And again, make sure you understand what is permanent set in these systems. All right. Sound good? Sound familiar? And then, of course, thermal transitions. And so you should know what TG is and how structure can control it. It's one of those abstract things which you should have at least a good intellectual handle on at this point. How does molecular weight control it? Free volume, chain flexibility, side groups, polarity, branching, cross-linking, plasticizers, crystallinity, pressure, heating rate. So you really need to know what TG is and how these factors can either impede or improve the glass transition in these systems. All right. Hopefully that's kind of all second nature at this point. We do have some copolymers and simple rule of mixtures for TG calculations. All right, that's really straightforward. Make sure you understand that. And then DSC Data Interpretation, and I don't mean going back and looking at DSC traces. I mean, if you look at this type of data where you have a single phase versus a two-phase structure, all right, what does that mean? And so I can have a copolymer, and if I have AB, 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 I'll get this one in the middle because it acts like a mixture. And if I have 100 units of A followed by 100 units of B, then I'll get separate glass transitions. As they can find themselves and self-associate, and we start to see these distinct features, even though the total amount of A and B in both of these systems could be exactly the same. And so how you arrange them in space controls how they behave in terms of their thermal behavior, and then of course it also controls how they behave in terms of their mechanical behavior. Any questions about that? And then, of course, if we talked about TG, we have to talk about TM. How does structure control that? And molecular weight, free volume, chain flexibility, side groups, polarity branching, cross-linking, plasticizers, crystal heating rate. All these things can make a difference in terms of what we experience in terms of the melting points for these systems. And again, it's going from, in this case, from a solid to a liquid. And a lot of these factors can still be important as we go to being a liquid. And then also the DSC data, interpreting DSC data, and the percent crystallinity calculations, which are really simple once you walk through them once. All right. So hopefully that's something that you guys are familiar with. And this is just showing you some effects of heating rate on these measured either TG or TM. I forget which one that is. It doesn't really matter. It all has to do with the artifacts associated with heating rate. Any questions about that? All right. And then last but not least, these systems of polymer solvents. All right. What is phase separation, and how does the free energy change in these systems control this? And so make sure you're not fuzzy about free energy control over these systems. You really need to have a clear understanding of this. I know we hit you with it over and over again in this major, so here's a great example of how it's important in terms of controlling structure. What do free energy plots of phase separation look like? What do the phase diagrams for phase separation look like? How does molecular weight affect the phase separation process? And of course also the effects of Brownian motion. All right, so make sure you understand what Brownian motion is. We all understand what Brownian motion is, yes? That's motion of brownies off of a plate. It's nothing to do with elves. All right.
What you said was basically the unpredictability of particles within a space.
Don't use the word particles. All right. So Brownian motion has to do with vibration. All right, and how this process of vibration will reverse things, and that's Brownian motion. In this context, we can talk about solvent particles.
Some random point, all the air in the room can condense into one area, right?
Yes, that's kind of Brownian motion. But we talk about how molecules impacting other molecules can move them around. All right, so we have air molecules constantly pounding on us all the time. We're too big to be affected by those air molecules pounding on us all the time. But if I'm a little virus particle that someone just exhaled, then Brownian motion can move that virus particle around. Speaking very directly, okay? And so it depends on the size of what's being hit by these random molecular impacts. With polymers, it can be other polymers that achieve the same thing, okay? Any questions about that? Okay, and then the lower critical solution temperature versus upper critical solution temperature, what's going on in those systems. And then nucleation and growth versus spinodal decomposition, the characteristic of microstructures and pathways. And I know this is a kind of advanced concept, but the key is to understand where it can go. The two different directions it can go to in terms of nucleation and growth versus spinodal decomposition. So how do we get from one to the other, making sure you can recognize the final structures, which should be pretty straightforward, and have some rough idea of how they develop. Spinodal decomposition is especially challenging to understand sometimes, and so, but just knowing where it goes and how it gets there.
It's So
is going to be important to us.
going
Yes,
by this, you will not ask us anything earlier than lecture 28 on the exam.
that's correct.
Except for the usual big 6 or whatever.
Do you want me to ask you the big 6 or just skip it altogether?
Yeah, skip it.
How many want to see a big 6 question? It's an easy point. It is. It is.
Well,
it
I
is
got
easy.
it wrong last time, so.
I think there's a slight majority for a big
Yeah,
6
I would
question.
just take a favor. If you already did vote, okay.
All right. I think the
We'll
big
do
6.
Big 6.
Big 6 up.
Easy
All right.
points.
Okay. It should be.
I'll say I don't mix up 2 and 4. again.
Should be. Okay. Yeah, that's the plan anyway.
Big 6 add the 7th.
And the 7th, of course. Yeah. Okay. Yeah. Big 6 plus 1. All right. So how block copolymers do or don't undergo phase separation, and the extent of this issue of separation, and hips. You know, keep coming back to that. You know, we've kind of had the old definition that we talked about early on, and now we kind of have the new one involving these advanced block copolymer structures where we cannot let the polybutadiene separate from the polystyrene. All right, that's essentially what that boils down to. Rather than just having loose particles, we now actually have bonding between these phases, but we let copolymers do what they can do, which is, if they're long enough, they'll clump together and form little islands of themselves. But here it's controlled using these copolymer chemistries. Okay? Any questions about all that? Any questions about the final exam? Anything we're unclear on? All right, well, I hope you guys feel like you've learned something since the beginning of the semester.
Actually, I have one small question
Yeah.
for the final exam.
Yeah?
Would you object if we brought a snack or drink to...
I have no objections to that, as long as it's not really noisy and loud and crunchy. So no celery, no potato chips. Anything else? All right, so I'll see you guys on Friday here, right?
Right here,
Yep.
12 o'clock.
Yep.